Thank you. I had a great introduction planned, but we already had a great introduction. So this is Stu. I'm Aaron. I'm going to take you through essentially what the issue is, the problem, and the way we deal with it currently. Sometimes you can get a little bit more complicated than what we'll show here, but in general, when it comes to diluting narrow veins, there's a couple of options that are more commonly used. And then Stu will take you through Entech's way of looking at using minor shape optimizer to improve the outcome, make it a little bit more accurate. So I think this way. So in terms of mining, I think everybody is pretty comfortable with how mines operate. So the idea of mining is obviously to get all of this pile of rocks, chuck it in there and put it somewhere where it's supposed to go. So that's probably the most important thing, is it going to the right spot? So when you're dealing with narrow vein deposits and then you blast it, all of that material gets kind of spread out a little bit and you get dilution. I know I'm preaching to the converted here, but once it's diluted, we then don't know when we put it in here, should it go to the waste dump or should it go to the ROM stockpile? So there are a couple of ways, as I said, that we deal with that. The one thing that we do is just apply some mathematical factors. We say, okay, we're going to blast it. We're going to spread this little narrow vein out. I'll give it, plus or minus this much. This is how much material is going to go in this pot. And I'll come up with a mathematical factor which has a bit more science than just sucking your thumb. You'll look at the widths of things. I'll explain that in more detail in a minute. Or you can reblock it. So we have a SMU size that is related to the equipment we're using, the rate of mining that we're going to be attacking this deposit with. So what size of block is that little narrow vein going to spread out into, because that's the smallest block we can chuck into the back of the truck and put somewhere. And then the last method is the method that Stu's going to cover, which is using the mineral shape optimizer to solve a couple of problems that we have with trying to do method 1 or 2. So just to describe the data, now this data will be available, I think. We're making it available. It's just a simple way to illustrate what's happening. So what we've got is we've got two veins. One's a little bit thicker than the other. They're reasonably vertical, but not exactly vertical. And as you can see from the plan view, they kind of wander across the landscape in the XY as well. So not ideal, but that's life. I don't think anyone's ever found a nice ideal deposit, or if they have, it's been mined. So we've got a couple of slices to illustrate what's happening here. So the blue slice, which is over here, shows you've got a bit of a gap between the two veins, and then the green slice at the bottom is the gap is quite narrow. Okay, so they're converging or diverging, depending on which way you're looking at it. And that vertical slice is what shows you what's happening. So we've got a good bit of width, which is more than your SMU up the top, and you'll get to a point where your SMU is going to come into play down the bottom, right? So also, I just want to point out our baseline for this. So if we just evaluated those veins, there's this many tonnes at that many grams per tonne. So if we're doing a mathematical dilution, it's really about taking that width, applying some extra width to it. There we go, thank you. Applying some extra width to it and doing some calculations. But one of the main issues we have with that is we've got two veins of different sizes here. So when you start thinking about your SMU size and you're applying a bit of a dilution to the wider one, it's kind of the same factor that's being applied to the narrow one. You can get a bit cute with the math, but certainly at a high level, people aren't really worried about that. They just chuck a dilution factor in, here's my multiplier on it, and modify away. So the problem we have with this is it can tend to undercall the dilution. So when we apply that, you'll see we get about 28% dilution from the factors that we've chosen there. So about a half metre additional dilution there. So as will be shown a little bit later, that can drive your pit optimization to be a bit bigger than what you really expect it to be. The other way is to look at reblocking. This is probably one of the more common things that people do, is that they will do the reblocking, but the main issue that you will have with reblocking is if it's not aligned perfectly to your veins, which it never is, then you have the potential, try and find a good bit where it shows it. So we've got this nice thin vein which is going to get spread out into this entire block. So you end up really exaggerating the dilution. So we've got quite a lot of dilution there. Now, exaggeration is good sometimes. In fact, some people might say it's the greatest thing ever in the history of the entire universe, but not when it comes to dilution. So I can resist that. So here we have way too many tons because we're just really not aligned. And this is just one slice. Obviously, it might be aligned in one area, but then deeper down into the ore body, it's not going to be aligned, and it just really oversells the dilution. So that's going to affect your pit optimization, obviously, because your cutoff grade for each SMU is going to vary. So I think I'm going to hand you over to Stu now, and I've lost the remote, who is going to take us through what the mineable shape optimizer, which people normally associate with underground, and in fact, I often hear it referred to as the stope optimizer, but it does have uses, practical uses, open pit. So I'll hand you over to Stu, run you through how this works.
Good, everyone. So using MSO, what we're looking to do is to simulate that mining parcel and adopting the expected mining parameters. So the dilution on the hanging wall and the footwall, whilst also observing any interstitial pillar distances. So in this scenario where previously we looked at the mathematical and the reblocking, what we're expecting to see is that for the two loads, we're honouring the half metre on the boundaries, but also honouring an interstitial pillar, which is currently set at 5 metres, and also a minimum mining width. So if you were to have a particularly narrow vein, you also want to make sure that it's physically mineable in its width. So for example, at the upper point up here, we've adopted a 3 metre, so 2 plus half metre on the hanging wall footwall. So the result, I'm jumping ahead to the results, but based on the previous figures, so the dilution in this scenario will actually fall somewhere between the mathematical and the reblocking. So what the goal of today is really just to show you how you can use this process and how it would flow through in the optimization as well. So in preparing this scenario, so it's a feature in Studio OP. So at the top here is the point of the ribbon. So you simply just navigate to the reserves and then the mineable shapes. And this will open up a ribbon where you can then start setting your parameters. So the parameters themselves are laid out here, but the key ones are really your cutoff grade. So the cutoff grade at the moment is set at 0.5, which I'll cover in the next slide about the optimization. The framework, though, are the mining or the SMU cell size. So we're looking at what strike, what width, and what height. So it'll ask you for the width and the height, which is set for 5 metre strike and 2.5 metre vertical height, so flitch height. And then the other parts that were just previously described, the minimum mining width and the hanging wall footwall dilution. The results, so I've highlighted two sections. So the result is shown in green here. At the top of the ore body, where the red line indicates, it's going to have 2 loads as they're sufficiently separate. And at the bottom, this will actually be one shape right across. So it's joined the 2. So next comes the bit where how do we get that information across into the model to then be used in optimization. So there's a couple of ways. I mean, you can look to sub-block the model to fit within the shape. the result of which is a very large model, as it will be very fine resolution to match the wireframe sizes. As depending on the size of the model, you can get tens of thousands of these shapes. An alternative is actually to use a mathematical fraction that shows a proportion line inside the shape or outside. So that's the trival function in Datamine. And running this, it'll create a new field, a mined field. And the result of the mined field is shown in here, where you have 100% of the cell lying within the shape, up to just a fraction of the cell lying within the shape. So it looks coarse, but that's really the native model, and then adopting this mathematical field. So actually, I must point out one sort of catch. So if the model itself, if the parent cell is larger on strike than the actual cells, we do need to subblock, or rather change the framework of the parent cell to match in the y direction the actual size of the shape, to prevent any cells from overlapping two shapes. So what we do is actually align the native model in its parent cell size to the y direction and the z direction. And then when we're running this trival function, all we're doing is actually analyzing it on the x direction. So there's no chance of the parent cell overlapping two cells in a y or z direction. And it's only on the x that it's actually calculating this mathematical field. So to illustrate what the effects of these different approaches are, I've just set up a very basic optimization, adopting the following parameters. So a mining cost that escalates as follows by depth, an all-in processing cost or ore cost of $40, a convenient revenue of $80, and 100% recovery. It's really just for illustration. It's so that we can say, okay, our break-even grade is just going to be 0.5 grams, and that's the parameter that was used previous on the cutoff grade for the shapes. So in setting up NPVS, all we're doing is we're actually using the same settings, all apart from one other factor. So for the MSO run, we're just using this mined field, which is the product of the trival, as an ore fraction. And because we've determined this break-even grade or break-even cutoff, we're actually not going to use where the parcel revenue exceeds the rehabilitation. We're actually going to say that everything that is defined as ore must be treated as ore. So what the result of that will be is any diluting waste on the perimeter which is flagged with an ore fraction will automatically go to the processing plant and attract that cost as well. So the results are here. Unfortunately, I've actually needed to update one of these, unfortunately. So the reblocked, as expected, is smearing the metal and grade too much, and we're seeing a very diluted model, and the result of which is a slightly shallower pit, and also delivered to the processing plant with a lower grade. And then the MSO one is, as we expect, slightly in between with the dilution factors in between and at a higher grade. And the last one, the mathematical one, unfortunately, I've used the undiluted ore tons here, so that should actually be about 120,000 tons. So we see a more diluted grade than this, but it's about 2.7. So we're actually going to strike. So the MSO one is striking somewhere in between. So I guess the takeaway is that you have to be very accurate in the narrow vein settings to achieve probably what you anticipate as the physical or the expected mining factors. It's a rather brief one. So the conclusion, I guess, these are the images of what we're seeing in the block model. So the reblocking, the MSO one, and then the mathematical one. The takeaway, I guess, if you're using those is, the best way that there's another way to try and represent these mining factors, and that's using this MSO method. That's it from me, but
that's it from us.
Yeah.
This is the two Ronnies. Does anybody have any questions?
I guess the obvious one is, did you manage to reconcile it, say the mill reconcile or even grade control? So was this based on reserve models?
So
grade control?
So this is the model itself. So you can reconcile it though. The ore fraction result, is that what you mean?
Well, with the three predictors that you've ended up, the three methods, how do they then compare to what you think actually happened in a real life situation? Did you reconcile, I guess, is the question.
Yeah, it's often a murky field. There's a couple of operations that have used this approach. One is Silver Lake, one Boiler Dam, and then it's more in study level that I've used this approach. So the reconciliation is probably not as rigorous as I'd like, but
so it was on reserve models because it used integrating.
No.
Question about the MSO. Is it a different module from the other download?
Yeah, so it does sit in the Studio OP. Pedro, I might say.
Actually, the same tool that you have available in Studio G and in Studio P as well. So it just depends how you find the setups and where is how is your frame and is the direction you like to optimize and do an image to get the best shape to find your next and applying this collaboration.
That leads to my second question on with MSO. There are three different methods to use vertical slicing, horizontal slicing, etc. Which method was used for?
So this one, just the vertical slicing on the YZ. Yeah, no worries. And as mentioned, all the data that's been used to prepare this is also available. So all of the script, and it's a very simple data set, so it's easily picked up and run with. It's available for you.
So I've got a question. How long does it take? Like comparable? Is it comparable to reblocking or?
So yeah,
exercise.
So yeah, we are talking about some big runs in MSO. So there are some tricks that you can use, particularly in the scenario. So because we're fixing the wall angles on the cells, I mean, we're not going to drill and blast, to sort of suit a varying vertical contour. We're really just looking at these small 2.5 meter flitch parcels. So you're locking that, and so by that, we're not really interested in what's happening above immediately. It's simply analysing on this 2.5 meter flitch. So what you can do is you can piecemeal your runs into the 2.5 meter flitches, and that will run and take up all of your RAM, and you can set that running multiple instances and totally absorb all the RAM in your machine, or you can run multiple machines, and that will then obviously take care of the time factor and just recombine the result later. So you can take a 30-hour run down to 30 minutes.
Can I ask a question?
For the presentation, we've used SSO, MSO, whatever it's called nowadays, product, on lithium deposits. It's really good for finding that, because they're not flat, they're not the old gold one. Really good for that. PGE deposit, I think we have run for days, very large one, cruncher and yet, so we've done a couple of gold deposits as well, which is good. And then obviously got better the normal lesson use studies and everything. But it's a good tool. It's what we found is predominantly our underground friends, sort of all of their domain, and they didn't like us logging on and using an SSO. But if it's something that you should. We like to think outside the box, and you can do your SMU studies and everything else, but this is another tool to just compare to see whether things are going right. So just because it's been designed for underground, so you can exactly get the scope and shape. Just call it the shape. So it's a really good product.
Thanks, John. Cheers.
I have a question. Have you ever thought to apply a variable cutoff grade over your fleets? Like as you're going down, if you like to apply different cutoff grade, not the.
Yeah, definitely. It's very flexible. So a way to manage that would be to, say, for example, you've got different weathering types, so you're going to have a different recovery and different cutoff. You simply just run between the approximate RLs. You can actually flag the cell with the dominant weathering, then you can filter that out and recombine them. So you'll never have, if you run with the same parameters for the weathering being dominant on each case, you'll never have overlapping cells, as it'll fall into one category or the other. So it's very binary in that sense, and then you simply just add them back together. So you can easily run to whichever cutoff you like. Yeah.
And how about your final report? Because sometimes you have some really narrow veins that you not consider as ore in your initial dilution analysis, but in your final report, do you run any second analysis to maybe increase this as a low grade or opportunity or marginal ore, or you just exclude this from your
So I think with the narrow veins, I mean, it's working on the cutoff grade. So I think if it's deemed viable adjacent to another thicker load, it would consider it. Otherwise, it's just left out.
This isn't specific to narrow vein in particular, but with MSO, is it possible to apply a negative skin? So you accept all losses in order to maintain like all value?
I am not sure. I have not attempted that, but I don't know. Do you, Datamine?
As this question to Andrea.
Yeah. So is there a negative skin that can be applied, say, inside of a boundary? I know that you can use the boundary for MSO runs, but can you go inside of that by defined distance?
I don't think you can.
Not sure.
No.
We can check for you, but initially it's a good question.
Yeah, I'm checking the questions here. Yeah, there's one from Cyril. He's just saying he's asking how MSO can guarantee the optimality of the limits of the mining scope, since it's a heuristic method of optimization.
So it comes down to your cutoff grade. So the grade is evaluated, and I guess it's inherent to all versions. So you're still going to have that same questionability of, if you reblock it, there's probably less control on the spatial distribution. I mean, this one is cutoff grade driven, same as the others. However, this time we're probably trying to align it to a desired shape. The reconciliation of those shapes can be conducted by looking at the MSO result. So the MSO triangle file or the wireframe file will actually contain the tons within the shape and the evaluated grade. So using that, you can then compare it back against a block model report using that mine fraction field. So you're able to at least to reconcile that part of it. Yep.